Hello everybody, my name is Jan Seifert. I'm product manager for Digimat software, and today I want to give you a brief demo for Digimat solution reinforced plastics. Reinforced plastics is a GUI environment which guides the user through the setup of a coupled analysis by reading in some FE analysis, associating a micromechanical material modeling, choosing a Digimat engine for the coupled run, mapping local fiber orientation, and finally launching the job and accessing the results of that type of integrative simulation. In the scenario that I brought to you today, I want to call it the semi-quantitative scenario. We assume that the FE analysis already exists. In this case, it will be a model set up in Mark-Mentat environment. Also, we assume that an injection molding simulation has been run, and we rely on a set of exported files for the information coming from that direction. We take a straightforward approach to material modeling, means that we will use a nonlinear elastoplastic material. And at that point, we will add some extra challenge, means that we want to perform a semi-quantitative reverse engineering based on ISO 527 type of measurements. Let's see how the user proceeds from that point, and we want to start with the material modeling. So material data certainly is found quite often in an Excel environment. So we have strain and stress values that we somehow need to bring into the Digimat environment. So we just copy those values from Excel, and now we can access the Digimat platform, and we will use MX, the material exchange tool. It comes along in the fashion of a database, and so we access the database, and we will use the import tool for experimental data, which has the option to import directly tabular type of data, and we paste the values that we got from our Excel sheet inside this import tool here. Once we have set some meta type of data, we can simply press import. So then we will have the data inside Digimat MX. We can show this type of data. We select it right away because we will want to use it later on for the reverse engineering procedure. And if we plot the data, we see it's exactly the curve, the graph that we wanted to have here. Proceeding with the reverse engineering means that now we need to choose a suitable material model, and as we have a PA6 GF30 material here, we can browse through the existing material models that we have provided directly with Digimat MX, and for room temperature we find that basically two models are interesting. One is a conditioned material, the other one is an unconditioned one, so we just add it to the plot to see which one would be best. And we see that the red and blue curves are quite close to each other, so certainly the blue, the conditioned material, is the material of our choice. So we just select it. And now we have two sets of data, one experimental, one material model, which we can bring to the reverse engineering GUI tool. And simply by now setting different material parameters, we can adjust the material model such that it matches the experimental curve best. So we simply click the analysis. Here we see the residual reducing, and here we can even observe the progress of the adaptation of the curves, and we already see quite some nice match of the curves, so we can expect that quite soon the run will be finished. Let's switch back to the residual, and we see that it accesses a global minimum of all tests run. So it's finished now. We see a good superposition of the curves, and we can simply now import the results into our database. So once we've done that, we can close the reverse engineering GUI tool. We can access the analysis files behind our grades, and we can just add it to the plot. And here we see the yellow curve now perfectly superposing the red curve, and that would basically be the micromechanical material model that we want to use further on. It's stored in Digimat MX, and now we can go to RP to proceed with our analysis. So for setting up the coupled analysis, let's pick up the user from his environment, in this case Mark Mentat, and simply what you do is you export an input DAG and write it to some location on your disk. So let's export mark.dat. And that's basically it. We can close the Mentat environment and now access Digimat RP. Here we load the model that we have just exported. And the task now is to associate a material to that model. So we add a Digimat material, and from here we can directly access the Digimat MX environment. We can choose the analysis file that is stored in the database and simply export and quit. And here the material properties will be directly taken over in RP for the coupled analysis. The next step is fairly simple. We now have to add the injection molding information. So we load the injection mesh. Then we load all the associated fields. Fields are local fiber orientation. So here we see display of that on the injection model, and now all that remains is to map those injection data onto the structural analysis. We use the integrated mapping method here, and right away we will find the data now on the structural mesh, so we see it here on the left side. Everything is well defined, so we can now submit our job. I run the job in a custom directory of my choice. And here I get an overview of all files that are required to run a coupled analysis. That would be a modified FE input file, the Digimat material file itself, and associated fiber orientation data. I want to run the job locally on all my 8 CPUs. I start it and I access the monitoring window of RP. On the bottom of the window, I can see all messages resulting from the Digimat to Mark interface, so I see it nicely up and running. And on the top, I will see soon a list of iterations, so basically the information that comes from the FE solver itself. On the very top, I can access different controls over the job, so I can view results, I can view an SDV table, open working directory, and terminate the job. The SDV table is quite of importance because here we use the user subroutine to Mark to communicate material data, but also at the same time we write certain user variables. And if we just browse through the list here, the history variable 28 is quite interesting. It's the accumulation of plastic strain in the material matrix. And such a result is a very typical result of a micromechanical analysis, and you will not find that kind of type of result with standard isotropic models. So let's wait until the job has finished. Once the job has finished, RP will automatically open a prompt that asks you to open the result file. So if I click yes, I will be redirected to my Mentat environment. So here we have the Mentat model again, and I can now directly access the results. I will add a contour plot. And here, if I look at the accessible results, I find my user-defined variables. And as stated before, let's access the variable 28, and let me just zoom into a region of the model of our interest. So if we run now through the results, let's look at the upper left corner of the model, and what we see here is a region where we have a high accumulation of plastic strain in the matrix, and basically this tells us this is a critical region, and the effect is that the underlying microstructure in the coupled analysis causes this type of behavior here. It's already the end of the quick demo that I wanted to give. So if you're curious now and you want to have more information about Digimat RP, please do not hesitate to contact support@extreme.com.